Okay, so let's have a quick review from last time. I guess we should start from earlier. So last time we go over this linear constant coefficient differential equation or difference equation. And the general form of the differential equation look like this. So it's linear because all those input and output. Okay, I guess first of all we are viewing this differential or difference equation as systems. So we have some x of t as the input to this differential equation, and this is an implicit system we want to solve for the y of t. And to solve a differential equation, you need to supply the auxiliary conditions. And usually it's kind of like solving many different variables. So if you have nth order differential equation, you will need n auxiliary conditions. And the auxiliary condition we consider here are those initial race conditions. So for differential equation, that means our y of t will be 0 until your x of t start being non-zero. And that point where we start having input signal, we call it t naught. And for initial rates, that will translate into the y of t naught and the dy dt as t naught, and all the way to the n minus y dt n minus 1. Those derivatives will all be 0, so it's quite smooth at the t naught point. And if the system is initial rates, then we prove that it will be causal and LTI. And back to the name, so it's a linear constant coefficient, means that those y here and x here are all first order. I guess I have no power, so it's just y and x. There is no y squared or x squared, etc. And it's constant coefficient because those ak and the bk are constant. They don't depend on time. And also it's nth order, means y has nth order derivative. So this is a differential equation, and we prove that it's linear and causal, but we have LTI and causal, but we haven't talked about how to solve them yet. We'll see that in chapter 4. And also there is difference equation. So it's like differential equation, except that we now have difference instead of differential. So instead of derivative, we just have time shift here. So we have y of n minus k and x of n minus k here. And once again, it's linear and constant coefficient. And nth order means this k goes up to n. And for initial rates, it means like there's no derivative in discrete time. So the initial rates is also different. Initial rates means that you look back the n time steps of y, and they should all be 0. Okay. And once again, this is causal LTI. And for difference equation, we do have a way to solve that. It's quite dumb, but you can solve it recursively. So you know that y of t stays 0 until x of t have something. So you can rewrite your difference equation like this. You can put all the y of n minus k to the other side for those k not equal to 0, and you have y of n on here. Okay. So you have y of n on one side, and you have all the things that depend on the previous time step. And you know everything is 0 until t naught, until n naught, because of the initial rates. So you just have y of n equals 0, then you solve y of n naught equal to whatever those things that comes before n naught will say. Okay. And so you keep solving those equations. So we have an example here where we have this x of n equal to delta of n. So this is n naught equal to 0. So you can solve y of 0 by doing this x of 0 and y of minus 1. And then solve y of 1 from x of 1 and y of 0, etc. So keep going forward. This is a recursive relationship. So you can solve this one step by one step. I guess one time by one time, and you will get the algorithm to get you the answer. Okay, so that's difference equation. And any questions so far? No? Okay, So hopefully we can finish chapter 2 today. Let's see if we can go really fast. Okay, and so a small wrap up for the differential and the difference equation is that we can write them as block diagram. Okay, so first we do this with difference equation. It's easier. So we'll try to have a system that will represent the difference equation by having those three components. So first is just addition. So you have one input signal, another input signal, you get another output signal. Output signal that's x1 plus x2. Okay, and another one is multiplication by some constant. So we write it as this. Just a line with the a here means that you input x and it will output with ax. So I guess technically we should write a block here, but the convention is we just write the a here, and you assume that you pass through this line and your signal will get multiplied by a. A is a constant. And now this one is more complicated. It's a time delay gate. So you have x over input, then your output with x over -1. So you do a time shift, and I believe this is a delay. Okay, and yeah, it's unit delay. And so how we use all those three things to get the difference equation as this: y of n equal to a y over -1. Excuse me, y of n plus a y over -1 equal to bxn. And okay, so we write this in kind of the recursive form. So we have y of n equal to whatever other things on the. So we put y of n on the left hand side, and everything on the other side. And I guess we didn't give a rule, but we have an example that will pretty much tell you the rule. I guess sorry. So for the later part of the chapter, we'll have more explicit rule. But here we just see an example. So we see we can express this in this block. So how does this work? So we have y of n as the output here, and it's a summation of two things. So one of them is just b times x over n. You see b times x over n here. Okay, so that's correct. And what's the other one? The other one is more complicated. So we know here is y of n, and here we have this forking, means that the input to this d is also y of n. And so y of n delayed by time step, divided by 1 time step, so this become y over -1. Then y over -1 times minus a, so this line here become -a times y over -1. Okay, so we know the output here will be a y over -1 plus b x over n. Okay, so we have here that the y over n should satisfy this difference equation. So y over n equal to bxn plus minus a y over -1. So we see that we can have if we can build this feedback system, then it can represent the difference equation. Okay, and that's the general feature here. Is that's the thing we should learn here. So yeah, so you have those implicit system where described by a difference or differential equation, then you can build a physical system that will give the same thing by having some feedback loops. Yeah. Because you see one side has y, another side has y, so you want some feedback loop. So you also have some y in the beginning. Okay. Okay. So that's a discrete time case, and for differential equation is similar. Okay, so we still have those addition element and those constant multiplication element. But now instead of difference, we have this differentiator that should have input x over t will give you output dx dt. And okay, so this is basically the same thing. So we're on dy dt plus ay equal to bx over t. Then you move everything except y to the other side. So you have y equal to 1 over a dy dt plus b over x over t. Then, and this is basically the same thing except the time delay. You have differential here. So you can see that this feedback loop also gives you a differential equation. So yeah, so if you want to build I guess this is what the double imager would like to do. So you want to have build some component that give you that represent the system that's represented by this differential equation, then you can build a circuit like this, and it will give you this XY input-output relationship. But turns out now we are engineering, and then we need to consider more practical issue. And it turns out that the differentiator is a very bad component to build. It's very unstable, and sensitive to noise. So instead of differentiator, we want to use integrator. So we rewrite this condition, and we put dy dt on this side, and we integrate it. Okay, and so we integrate both sides, and we have y of t on this side with some boundary condition, I will assume. And then we have, well, integration of this bx minus ay. Okay, and yeah, and so this is other circuit the circuit we want to use to build this differential equation. So we have y of t, so y of t is here, will equal to the integration of, so here we will have bx minus ay because it's y, so here this is minus ay, and here with bx, so here is bx ay, and then we have integration. So y of t equal to the integration of bx minus ay. So that's an example of how to express differential and the difference equation as block diagram. And I think later part of the course we will have more complicated example of those. Any question? Otherwise, we're going to into the total differencing and the intrinsic part of this course. And I think this will be the last one we talk about in chapter 2. Okay. The later materials are, it actually depends on the version of the book. So I think in the new version of the book, it's not even in the book for the multivariable part, etc. But anyway, I will keep the slide here and you can read it, but we will probably not discuss it in class. So after singularity functions, we also have like multivariables and like edge detectors, but they are not like very important for the follow part of the course. So I will leave the slides online and you can read them. But they are probably not tested. But okay, and I will not spend time cover that in course. But anyway, today we will talk about singularity function. So what are they? They are basically delta function and their families. Okay. So first we start talking about some properties of a delta function. And remember we have shifting function looking at this. So we say the delta function will pick up the time value of x of t at the t0, okay? Because it has 0 everywhere else, and it just multiplies x of t at the t0. And so if we take the integration on both sides and change some variable, then we will arrive at x of t equal to x over t convoluted with delta of t. This is something that we say you can check it yourself, and here we derive it once again. Okay, so delta of t will be the, and so we can also interpret this as the LTI system, right? So delta of t will be the impulse response to identity channel. Okay, so that also makes sense, right? Because you put delta of t into the identity channel, then output will be delta of t. Okay? And you see this is what happened in an identity channel. So x of t convoluted with the h of t, which is equal to delta of t, then you go back to x of t. Okay? So this is describing a channel that output equal to the input. And everything makes sense here. And also similarly, a thing that we kind of used before is that x of t minus t0 will equal to x of delta of t minus t0. So this can be similarly described here, or you can just think of this as like, because here we have a LTI system, and so if you swap the delta and the x here, and actually it's a little weird. But anyway, I think you can derive this similarly, and you'll get that this is true. Okay, so this is actually identity we need to use. But anyway, what we want to say here is the other thing. So those are some property we want to talk about delta function. Yeah, and okay. So delta x of t equal to x of t convoluted with delta of t, and what's happening here? Anyway, so here we should also have delta. Okay, so this is delta, and so if we put x of t equal to delta of t, then we have delta of t equal to convolution of delta of t with delta of t. Now that sounds a little weird. And if we look at this thing with the triangle function, so remember we define delta of t as the limit of triangle go to 0 of this delta subtriangle. Okay? With delta subtriangle look like this, it has height 1 over triangle with triangle. Okay? And so we think about this function. So what is the convolution of delta triangle with delta triangle? And if you do the overlap thing, and they will find out that it's actually a triangle. So it's this function we call R subtriangle, and it's a height also 1 over triangle, and it's width 2 triangle. So the area is also 1, but is instead of rectangular, it's a triangle now. Okay, and so we have. So this is just this is just true for any delta. You just do the convolution of 2 of those delta subtriangle, you get this. And now you think about taking the triangle go to 0, then those two things should become delta of t because we define it that way. And the other side we have R subtriangle. Okay. And so R subtriangle, as triangle goes to 0, should become delta of t convoluted with delta of t. And because we have this up here, then that should equal to delta of t. So you have found out that this R subtriangle, when the triangle goes to 0, also becomes a delta function. Okay, so what we trying to show here with a whole bunch of things is we just say there are a lot of things that whose limit will become a delta function. So you see this delta of triangle is limit goes to delta function, and this R subtriangle is limit goes to delta function. And actually, like if you shift this a little bit, so if you, for some example, if you shift this thing to like here, right? So instead of from, if you were delta of triangle, you have like the function that's from minus triangle to 0 instead of 0 to triangle, or even minus 1/2 triangle to plus 1/2 triangle. Okay, so those kind of things, when the triangle goes to 0, it all goes to the delta function. So as a little spoiler. So whatever, so your function just need to look like an impulse. So you just need to have area should all stay 1, and you should have a very short impulse that is area 1. So its width should go to 0 as your triangle goes to 0, and the height should go to infinity, and the area should stay 1. Whatever those kind of function you have, and you take a triangle go to 0 limit, it will become a delta function. And so we have multiple examples of trying to convince you this is true, although we don't have solid proof. So here is one example. So we prove that this R triangle also go to delta function when triangle goes to 0. And here is another way to convince you that our triangle goes to delta function when delta goes to 0. So we consider this differential equation, and we have solved this before. So dy dt plus 2y of t equal to x of t, and we consider this. So this system with different input x of t, and so we want to see what happens when x of t equals delta of t, and we do this by approximating x of t with different function. So either approximating x of t with delta sub triangle, or approximating x of t with r sub triangle, and we just plot the result. And you can see so you can see we have different variable triangles. The triangle equal to 0.25, 0.1, 0.025, and 0.25, 0.1, 0.25. So you can see when we have a little larger triangle, they look different, but as the triangle goes to 0, they all go to this exponential function. Okay. So we're trying to say x over t, we approximate it going to delta of t with different triangle function, and we'll get the same result. Okay. So what do we have? Okay, and here we have more functions. So we even have delta of triangle convoluted with r of triangle, or r triangle convoluted with r triangle. Okay. So yeah, so those are also different functions, but you can see that for all of them, when triangle goes to 0, they go to the same thing. Okay. And there are more discussion here where when do you start to look like how small is the triangle? Is it small enough? That will depend on the coefficients in your differential equation. But anyway, we take triangle goes to 0, and we claim that when triangle goes to 0, it doesn't matter which function you are taking x over t with. It should all become the same limit. So we think they all have the same limit of delta of t. Okay, so we prove the property of delta of t being that, so I guess let's sort out the logic once again. So before we define delta of t as the limit of those delta of triangle, which is this rectangular, as triangle go to 0. But here we argue that you don't necessarily need to start with the delta of triangle. You can start with different things, and that have this unit area and look like a short impulse. And you take them with triangle go to 0, they all become delta function. And actually there are other ways to define delta function. So we can also just define delta function with this operational meaning. So we can also just define delta of t as whatever signal that when you convolute it with x of t, give you x of t for any x of t. Okay? This is we just proved, but we can move things around. So mathematically this works. You can just define delta of t as something that satisfies this. And this is quite nice. So we check that this is consistent with what we have. So you can see that you do like delta triangle or triangle thing. Typo here. This typo. Let me close this. Okay. But anyway, so those things when you take delta of 0, you take triangle go to 0, they will all satisfy this. So this is the operational definition. That's very nice. Okay. And you can also have other operational definition with this. So let's skip the derivation here. So you have this thing, then you can do a derivation like you define some function g of t. You have arbitrary function g of t, then you see g of minus t equal to g of minus t convoluted with delta of t, and you write out the convolution. Then you find out that g of 0 will equal to integration of g of tau, delta of tau, d tau. So this is like a shifting property. So you multiply g of tau with delta of tau, then you integrate over. You will always pick out the g of naught. So we can also think this as another operational definition of a delta function. So we see a delta function here. So you can also define your delta function as a function where you multiply it with whatever function, and it will pick out the 0 of your function. Okay? And skip so we just do the derivation from this convolution to this shifting property. And skip the detail, you can check these details later. So we can also derive the convolution from this shifting property by doing some smart choice of your function and the change of variable. So you can get x of t equal to x of t convoluted with delta of t. Oh, I also typo here. Wait, is that? That's probably a wrong start. Okay. Anyway, yeah. So x of t equal to x convoluted with delta of t. And you can also check all the other property of delta function works with those definitions. Okay. So that's very nice. we can think delta function with those operational definitions. Okay. And anyway. Okay, yeah. So we have a whole bunch of properties. You can check them when you're at home. Okay. And yeah, so for things, so you see that here we derive back to the 15 properties once again. So there are a whole bunch of definitions. We'll see they are inconsistent. But I guess for the doing test purpose, you just need to know that those are properties your delta function satisfy. You convoluted delta function with whatever function get to the same function, and also it has those 15 property. Okay, so this is also 15 property with our integration that we start with. And anyway, so let's go to the actual interesting part of this course, this class today. So it's the uni-doublet function. So it's a very interesting function. It's a derivative of delta function. Okay. And okay, so how do we kind of define this? So we start by consider this LTI system. So we consider a system where the input is x of t. Once again, input is x of t, output is y of t. And the system is just defined by y of t equal to dx of dt. So this is a LTI system, right? So because dx dt is linear, you put ax1 plus bx1, bx2 here, you get a y1 plus by1. And this is also the time invariant because you do a time shift, then dt equal to dt minus t naught. Okay, so this is an LTI system. Okay, it's an LTI system, so there is a uni-impulse response h of t for this system, right? We've been talking about this for the whole chapter. You have an LTI system that is characterized by its uni-impulse response. And that's when you put a delta of t as the input to this thing. Okay. So what happens? So you put delta of t into the input of this system, then you get this weird thing, the delta of t dt. Okay. So it looks very ill-defined, but we pretend it's defined. So just write it this way. Okay. And we give it then as u1 of t. Okay. So the h of t of this system will be this u1 of t, which is equal to d delta dt. This is just by definition. It's a uni-impulse response for this system, meaning that you put the delta function of this into as x of t. Okay? And okay, and so this is a very singular thing because you are differentiating. Remember, delta function has an infinite impulse, so you are differentiating infinite high impulse is very singular. But what property can we get? So property we can get is that for any x of t, then dx over dt will equal to x over t convoluted with this u1 of t. And to see this, you see that, so from this system, you see, so whatever output y of t equal to dx over dt, right? Because it's just this system. But now we remember this is LTI system. So LTI system, we always can represent it as a convolution. So this y of t should equal to x of t convoluted with the uni-impulse of this system, h of t. And we know h of t equal to u1 of t. Okay. So this is just x of t convoluted with u1 of t. And then we see that this part, this dx over dt, should equal to x of t convoluted with u1 of t. This should be true for any x of t. So we see that this u1 of t kind of describe differentiation you convoluted with it with any function, it gives you a differentiation of your function x of t. Any question from this derivation? So that's the important part here. Okay. So yeah, this is the important thing we want to talk about. And yeah, so this is del u1 of t defined by d delta dt. Then we see that x of t, when you convolute u1 with whatever function, it gives you a differentiation. Okay, that's very cool. And you can even do this more. So you just derive this very important equation that dx of t equal to x of t convoluted with u1 of t. And we can even do this on two derivatives. Okay, so what about d squared x of t dt squared? And this is also an LTI system. And we can call its unit impulse as u2. And well, you see that because differentiation is just twice this, you can think about this doing twice. So d squared x dt squared is dx dt, then do another d dt. So the first d dt will give you u1 of t, and then the second d dt will give you another convoluted with u1 of t, because you are doing this system twice. So whenever you do this system, it's same as you convoluted with u1 of t. Then you do the system another again, then you convoluted with u1 of t again. So you see that u2 of t equal to u1 of t convoluted with u1 of t. And on the other hand, we can do the similar thing here. So u2 of t is the impulse response to, okay, so we should write out the system. So now we are thinking about the system of y of t equal to this thing, right? Y of t equal to this. So if you think about this system, so u2 of t is the impulse response of this system. So just like what we do here, then we see that u2 of t should be, so we should have u2 of t equal to twice derivative of delta of t, right? Because you put delta of t into the system. So we derive that is twice derivative of delta of t equal to u1 of t convoluted with u1 of t. Okay, this is what we have here. Okay. And yeah, so so you can probably see that. Then you can also have like, so we have u1, u2, then we can have u3, u4 all the way to uk, and they will all follow the similar property. So the uk of t will correspond into dk's power x dt to the k equal to y of t, and so it will equal to the k's derivative of delta of t, and it will also equal to u1 of t convoluted k times. Okay, so we have all those very singular functions that will represent the unit impulse of those differential systems. Okay, very cool. You can see. So u2 of t, you convoluted with some x of t, give you the second derivative of x of t. Then you have x of t convoluted with uk of t, that give you the k's derivative of x of t. Okay. So those are like the operational derivation of those u2 to uk. And we can also kind of justify those from the limiting point of view. But as you see, it will be very singular. So we say u1 of t equal to dt delta of t. Now we think about delta of t as a limit of our favorite delta triangle. So remember, delta triangle look like this: is height 1 over delta, and width delta. Then you try to do derivative of those things, and then you see that even when triangle is not equal to 0, you take a derivative of this, you still already got something singular, right? Because every continuous part, the triangle, this delta subtriangle has derivative 0. So only derivative non-zero part on the t equal to 0 and the t equal to triangle. And the height will be this 1 over delta times the delta function, and minus 1 over delta times the delta function. So this is a very singular thing. Even when triangle is not equal to 0, you will have these 2 deltas back here. Okay? And okay, so u of t when delta not equal to 0 look like this already spiking thing. And we want to say it makes sense because we want to say when triangle goes to 0, we'll get back to this operational definition we have. We want dx of dt equal to x of t convoluted u1 of t. And okay. And then we try to do this. So we convoluted our x over t with our u1 of t, which is when this triangle not equal to 0. Okay. So x over t convoluted with this delta triangle dt. Then because it has 2 delta function here, and as we said before, it's start of this class, and we have x convoluted with delta function, and it just give you x back with maybe a time shift. So those 2 spike will give you x of t minus x of t minus delta, and then we have 1 over delta here will become this 1 over delta here. Then you see that when triangle not equal to 0, this becomes x of t minus x of t minus delta. Sorry. Okay, that's presumably this is correct. Okay, x of t minus x of t minus delta, and 1 over delta. Then when you take the delta goes to the 0 limit, you see that this is the definition of dx dt. So here we try to justify that this thing makes sense as the limit of those delta triangle formulation when triangle goes to 0. I guess you can also get a less singular derivation here. So here we have a derivation where our delta of triangle is rectangular. That's why we already have those infinite spike here. But if you use the R of triangle here, then you can have the rectangular here. Then the derivative will be constant, and you will get a less singular derivation, but the thing should work out the same. Okay, and so here's the thing to convince you that's true. But anyway, so the thing to remember is that we can also just see this u1 of t with this operational definition. This is the thing we care most about. That is, once again, x of t convoluted u1 of t become dx dt. And you can derive all the property of u1 of t from here. So for example, you can see that if you integrate u1 of t with another g of tau, so u1 of tau with another g of tau, and that will give you a derivative of g of 0. So this is kind of like the shifting property of delta function, but you will get a derivative because you are doing this u1, and also this is negative. Okay. And also you will have that if you integrate, so you just take this thing and put x of t equal to 1 here, then we get that you integrate this u1 of t through everything, you get 0. That makes sense, right? Because you have an infinite spike here and the same infinite spike with negative direction, so those two things. So integrating over this thing, it should become 0, so those two should cancel out. Okay. Yeah. And anyway, so that's the operational definition. That's the most important thing you need to remember. And you can derive a lot of properties, and you can see more in the problems. Okay. And finally, so those U families, they are the other side. Okay. So this is a confusing notation, but so those doublet and triplet, so those U2 to U casing, they are corresponding to the system which are differentiation. So the other way of differentiation is integration. So we can also look at the unit-impulse response of integration, and that's actually something we already know. That's a unit step function. Okay. So if you have this LTI system where y of t is the integration of x of t, and we already see that the corresponding impulse response will be this unit step function. We already know. So let's just draw the unit step function once again. Now this is not singular because unit step function is well defined everywhere. Okay. So we have a unit step function that look at this. Okay. So it's 1 when t is bigger than 1, and 0 when t is less than 0. Sorry, 1 when t is bigger than 0, and 0 when t is less than 0. Okay. So that's a unit step function. And so we can write the operational definition that we for this system, then we see that x convoluted with u of t will be the integration of u of x, integration of x. Okay. And so just like the differentiation, we can also think about integration in more orders. Okay. So we can also think about what about the system of you integrating x twice? So you integrating x from to tau and to t. Okay, and that will be same as you convoluted x with u, then convoluted x with u once again. Then we call this u convoluted with u as u minus 2. Okay. And once again, this is not singular. You can just do the integration. And so u of t is a unit step, and u minus 2 will look like this. T is just a linear function, t times u of t. Okay. And so you can see this go to k's power. They are all non-singular. And we call those u sub minus k. Okay, yeah. So they are all non-singular, so they are u of t convoluted k times, and it's like a polynomial, so it's t to the k minus 1 power times u of t, and divide by k minus 1 factorial. You can just check the integration is correct. And you have x convoluted with u minus k will be x integrate k times. Okay. And so we have those. So we had the u of k, and now we have u of minus k, and we can actually put everything in this single family, so of u sub something. And we see that delta function should be u sub 0, right? Because you convoluted x of t with delta of t, then nothing happened. So that's so anything plus 0 equal to anything. So delta is u sub 0, it do nothing. And now we have a very confusing notation here. So u of t, if you are talking about u sub k family, is u sub minus 1 because it's corresponding to integration. Okay. So this is a little confusing notation, but that's just what happened. So remember u of t equal to u sub minus 1 because you convoluted your x of t with u of t. Here, you convolute x of t with u of t is the integration of x of t. And so our sub k, we are basically tracking how many derivative we have, how many times derivative we are doing on x of t. And because you convoluted with u of t, it's actually integration, so that's doing -1 times the derivative. And you can check that this notation makes a lot of sense because so whenever you are convoluting to u sub k, they add up. So for example, if you have u of -1 convoluted with u of 1, then it becomes u of 0. Okay. And yeah, so you can just check this is true. And in general, you have u sub k convoluted with u sub r, and it will become u sub k minus r. And those k and r can be anything. It can be from negative infinity to positive infinity. Okay, so this k and r can be anything, and this will be true. And finally, this is the page that summarizes all the things that you should remember about our unimposed and singularity functions. And yeah, so we have 2 more minutes. Let's see how you want to know. I guess we can see through this. So some property of the delta function. So delta function, you integrating over it, it becomes 1. And you integrate the delta function, it will be you integrate the delta function to some t become a u of t, and so you integrate delta function become unit state function, you differentiate unit state function become delta function, and we have the convolution property that we say at the beginning of the class. And then the delta function can convolute with itself, is still the delta function. And then we have 2 forms of shifting property. So either integrate it and it give you the f of t naught dot, or you just multiply it, then it becomes f of t naught multiplying your delta function. Then we have this really weird unit doublet that's very singular, but it's defined as the derivative of the delta function, and this u1, if you convoluted it with x, it gives you dx dt. And then you can do this even in case power. So you convolute this u1 k times, it becomes uk, and it will represent the system that's a case derivative of your x of t. And the other way around, you can have the unit impulse for the integration. And so the -1 time is just this unit state function u of -1. And those are all non-singular because they are just basically polynomial. Is t to the kth power times u of t, t times k minus 1 power. And when you convolute it with x, it becomes the case integral with x. Okay. And I guess the important thing we didn't say here, but also another important thing is for whatever r and k, u of k, u sub k convoluted with u sub r become u of k minus k plus r. And yeah, then we have something about multi-dimensional thing, but basically just saying us the one-dimensional thing, but there are more dimensions. I don't think everything interesting happened here, and you can read it. And on Friday we'll start on chapter 3. Okay. And yeah, the important function we talk about, and they are edge filters, which are kind of interesting, but not too essential for later part of the class. Okay, no question. Then see you on Friday.